Good day, students. Welcome to Mathgotserved.com. In this clip, we're going to be going over question number 2 of the 2019 AP Calculus free response questions. In this presentation, we're going to be focusing on position, velocity, and acceleration of an object traveling on a straight line. Question number 2 reads, the velocity of the particle p moving along the x-axis is given by the differentiable function v sub p, where z sub p of t is measured in meters per hour and t is measured in hours. Selected values of v sub p of t are shown in the table above. Particle p is at the origin at time t equals 0. Part A question. Justify why there must be at least one time t in the interval 0.3 to 2.8 at which v prime of t, the acceleration of the particle p, equals 0 meters per hour. So in this problem, we're being assessed on our ability to use the mean value theorem to solve problems involving linear motion. Okay. Alright, so before we get started to show that there is a C that satisfies this condition, let's go ahead and write down the theorem or formula that's going to guide our problem solving process. Alright, there are two things to keep in mind. The first one is the MVT, okay, your mean value theorem, or MVT, okay? Alright, so let's go ahead and take a look at what the MVT is. It's as follows. So let's take a look at the hypothesis of the mean value theorem. There are two conditions that have to be satisfied, okay? So let's look at MVT on function f, okay? So if f is continuous on the closed interval, so first condition is continuity on the closed interval AB, and we have differentiability condition and differentiable on the interval, on the open interval AB. Alright, so this is the hypothesis or initial conditions for the MVT. Alright, so for the conclusion, we have then there exists a C in this open interval AB where the average rate of change on AB, which is V of B, or what we're using F in this case. So there exists a C in AB where f of B minus f of A over B minus A, so this represents the average rate of change or the slope of the secant line on the entire interval, okay? The average rate of change is equal to the instantaneous rate of change at that particular C value in the interval. Alright, so this is using f of x. In our particular example, we're going to be using V instead of f. So, in this situation right here, we're being asked if there is a t in this interval that justifies the conclusion that v prime of t is equal to 0. So if we can show that the average rate of change on this interval is 0, then by the MVT we can conclude that there is a t where v prime of t is equal to 0 because it satisfies the initial condition of the mean value theorem. Okay? Alright, so the steps that we're going to employ in this problem are as follows. So number 1 is we want to find the left side of the MVT, okay? The conclusion side of the MVT. So we want to find the average rate of change, the ARAC, the average rate of change of the velocity function, okay, on the given interval. And then when we're done finding the average rate of change, we're going to use the MVT conclude that there's a t, okay, to conclude that there is a t, that we're looking for. Okay, so let's go ahead and get started. So we're going to start with the first part, which is to find the average rate of change of the function. Alright, so we're starting with the problem right now. So we want to find the average rate of change of the function, find the error of the velocity function on the interval 0.3 to 2.8. So what is that? This is equal to v of 2.8 minus v of 0.3 divided by, so this is v of b minus v of a divided by b minus a, which is 2.8 minus 0.3. Okay? And then you use your table to find v of 2.8 and v of 0.3. You're going to get 55 and 55 divided by 2.5, and then you get the average rate of change of 0. Okay, so this is the slope of the secant line. It's a horizontal secant line. Okay, alright, so what can we conclude based on this? Well, since this scenario we're dealing with satisfies the hypothesis of the MVT, how do we know? Well, it's a differentiable function on the closed interval, so that automatically means it's continuous and differentiable. So we know for a certainty that it should also satisfy the conclusion. So the average rate of change is 0. Then what do we know? There has to be a t in this open interval where the derivative of the velocity or acceleration is equal to 0. Alright, so step 1, we found the AROC, average rate of change, and now we're going to use the MVT to arrive at our desired conclusion. Alright, so what we're going to say? We're going to say the following: by the MVT, or the mean value theorem, let's write it out, by the mean value theorem, there exists a C in this open interval 0.3 to 2.8 such that the instantaneous rate of change v prime of particle p at C is equal to 0, because the average rate of change is equal to 0, and by MVT the average rate of change is going to be equal to the rate of change or instantaneous rate of change for some C value in that interval that you found the average rate of change over. Okay? Alright, so this problem is a 2-pointer on the AP exam. You get 1 point for finding the average rate of change, and then you have another point for explaining how the mean value theorem helps you to arrive at the desired conclusion. This problem gives you a total of 2 points. Alright, let's take a look at question 2b. In question 2b, we are being assessed on how to use a trapezoidal sum in linear motion calculations. It is use a trapezoidal sum with 3 subintervals from 0 to 1.7 to approximate the value of the integral from 0 to 2.8 of v sub p of t dt. Okay, the velocity of particle p. Alright, so let's go ahead and write down the formula that's going to guide our problem solving process. Now we're going to be using the trapezoid sum for this, the trapezoid rule, but I'm going to adapt it slightly to this particular problem. Okay, so let's say we want to find the integral. This is the exact integral. Okay, the integral from a to b of f of x dx, which represents the area between the curve and the x-axis. The integral can be estimated using geometry, right? You can estimate the integral using rectangular approximation or trapezoid approximation, left, right, midpoint, or trapezoid. In this case, we're using trapezoid approximation. So let's say we are using, so I'm going to call trapezoid T sub 3. What does this mean? Trapezoid with 3 sub-intervals. So if we're doing a trapezoidal approximation with 3 sub-intervals to estimate this integral right here, is going to be 1/2. So all the trapezoids are going to have 1/2 in their formulas, okay? So I'm just going to factor out that 1/2. So for each trapezoid is 1/2 sum of parallel lines times height. Half sum of parallel lines times height over and over again. So for trapezoid 1, it's going to be 1/2 b1 plus b2 times height 1, h1. That's for t1. For t2 is going to be this 1/2 times b2 plus b3 times the second height. And then for the third trapezoid is going to be b3 plus b4 times the third height. Okay? Can you visualize what is happening with this formula? It's very important that you have a visual understanding of what's going on. You don't just want to randomly memorize the formula. You want to understand exactly what's going on. So let me give you a visual representation of what's going on here so you can understand exactly how this works. You do not have to draw a graph every time. There's some shortcuts you can use with the formula to easily determine what the trapezoidal sum is. We're going to be going over that in a second. Okay, so let's say we have a function. This is an increasing function. Okay, so it's something like this. And then we want to use 3 trapezoids. So this is going to be the first x1, x2. So we have 3 intervals, 1, 2, 3, 1, 2, 3, and then the last one right here. And then let's say this function is going on forever. Okay, so you have your first trapezoid, your second trapezoid, and your third trapezoid. Okay, so this is T1, T2, T3. So for each trapezoid, notice you have 2 parallel sides and a base. Alright, so this represents the height, H1, H2, H3. And then you have B1, this is the first base, B1, B2, B3, and this is B4 right there. Okay, so the area of the first trapezoid, A of T1, is 1/2 B1, this base plus that base, B1 plus B2 times H1. That's the first area. And then the area of the second trapezoid is 1/2 what? Notice that the second side of T1 is the same as the first side of T2, right? So it's going to be B2 plus B3 times H2. That's for the second trapezoid. And then for the third trapezoid is 1/2 B3 plus B4. And then when you combine these, when you combine these 3 formulas together, you get exactly this. I just factored out 1/2 because 1/2 is common amongst all 3. Okay? So T3 is basically A of T1 plus the area of trapezoid 1 plus the area of trapezoid 2 plus the area of trapezoid 3, and this is what approximates the integral. Okay, so we have that down. Now let's do some work with the table. As indicated earlier, when you're solving the problem using the table, you don't have to write down the formula. Remember that time is of the essence in the exam, so you want to go as fast as possible, okay? So just using the table, you can label everything that you want and then just jump right into the trapezoidal sum. So you just have to remember that the difference on the independent variables represents the height. Okay, so the heights are on the independent variables, okay, and your bases are on the dependent variable. Alright, so we need 3 heights, so we're going to go from 0 to 0.3 is your first height. from 0.3 to 1.7 is your second height, and then from 1.7 to 2.8 is your third height. Remember, we're looking for the integral from 0 to what? 2.8. This is what we are estimating. Okay? Alright, so we're going to be subtracting here. So just subtract, subtract, subtract. That's the operation. So the first height, subtract these two, h1 is going to be 0.3. h2, subtract these two, is going to be 1.4. And then subtract these two for h3. h3 is going to be 1.1. Okay? And then our heights, our bases, b1 plus b2 plus, it goes on and on. Alright, so for this particular case, this is b1, this is b2, this is b3, and this is b4. What are we doing with the bases in our formula? We're adding them, right? So all you do is you're just going to add these ones, add these two, and add these three. These two right here. Okay? So that b1 plus b2, just add these two, that's 55. b2 plus b3, just subtract those two. You get 26. So you get 26 here. And then this one you get 26. Okay? Alright, so let's put it all together. So if we put it in the trapezoidal formula, this is going to be approximately, it's not equal, it's an approximation, is approximately, so we already factored out the 1/2 of b1 plus b2, we already did the math, 55 times h1, which is 0.3, so just multiplying the sums by the heights, piece of cake, right? And then the next one, 26 times the height, 1.4, plus the last one, 26 times the height, which is 1.1. And then go ahead and plug that into your calculator to get your final answer. Alright, and then when you plug it into your calculator, you should get, it's gonna be it's gonna be 40.75. Okay? Alright, so there you have it. This is the answer. Okay, what's the unit for this? This is meters. So this is just a side question. It's not, it wasn't asked in this problem. What does this integral right here, what does it represent in the context of this problem? What does this integral represent? Now we're integrating from a to b of v of p dt. This represents the displacement. Okay? There is position, which we'll do later on. There is distance, which we'll do later on, and there is displacement. Okay? Those are three formulas that many students often confuse. In this particular case, what we just found is the approximate displacement on the interval 0 to 2.8. Okay? So please do not forget the integral from a to b of v of t dt is equal to the displacement. And then what's the distance? Well, I told you we're going to do it, but let me just show it to you. If you take the absolute value of the displacement, you get the distance. Displacement is a vector quantity. It has magnitude and direction. Distance, on the other hand, is a scalar. It just has magnitude. You can never have a negative distance, okay? It's just like time situation. So it's just a side point to keep in mind. Alright, let's take a look at part 2c. And part 2c, we're going to be assessed on how to calculate the distance traveled given the velocity function. Okay? So it reads, a second particle q also moves along the x-axis so that its velocity for 0 to 4 is given by this function right here, meters per hour. Okay, so this is a totally different function. We're no longer dealing with p for this particular part. Find the time interval during which the velocity of the particle is at least 60 meters per hour. Find the distance traveled by the particle during the interval when the velocity of the particle is at least 60 meters per hour. Okay, So at least just basically means that we're looking for the time when the velocity is 60 meters per hour or greater. Okay? Alright, so in this particular problem there are two parts to it. So let's break it down in steps. So first part, or the first step, is we're going to find the interval. Let's call it AB, where what? Where the velocity of particle Q, V sub Q of t, is greater than or equal to 60. That's what at least means. It's 60 or greater. Okay? And then secondly, we're going to find the distance on the interval. Find the distance traveled by particle Q on that interval AB that we found. Alright, so next thing is the formula for finding the distance. Ladies and gentlemen, we just talked about it in part B, so hopefully you it's fresh in your mind. What's the formula for distance? So the distance traveled on an interval AB is related to the displacement calculation. So the interval from A to B of V of t dt, what is this? This is the displacement, right? But when we throw in the absolute value, that gives us the distance. So this is what we're going to be using for this particular problem. Okay? Alright. So let's do the first part. We're going to find the interval where the velocity is 60 or greater. So find where V sub Q of t is greater than or equal to 60. So we are constrained with the t interval, the time interval. It says from 0 to 4. Okay, so from 0 to 4. Alright, we're going to fire up our calculators and do this. So I'm going to be using the TI-89 to do this problem. Alright, so first things first, what I'm going to do is I'm going to store this function in my calculator so that I don't have to keep typing it over and over again. Okay, alright, so let me show you how to store it. So you just have 45 times the square root of t cosine 0.063 t raised to the second power. Okay, so that's the function. Let me just enter it just to make sure that what I entered is correct. So 45 over t cosine 0.063 t squared. Okay, so I'm going to store it. So you see your store button right there. So I'm going to store it in v of t. So store in v of t. So alpha v, where is v, where are you? Right here, v of t. Okay, done. So let's just call back v of t to make sure that what I stored is actually there. So that's v of t. Press enter. Looking good. Okay, so now I have it stored. I'm going to need this function for part D also, so if I have it stored already, it's going to be a piece of cake. I'll just use v of t to do my calculations. So let's see, we want to find where this function is greater or equal to 60. So we're going to use a graphical approach here. I'm going to graph this function and graph this line, this horizontal line, and then see where it's greater. So to graph it, I'm going to enter what? Enter v of, this is a function of x, so just replace your t with x. Do not type in t as a independent variable in the graphing window. You'll have a syntax error. Okay, so whatever function you have defined on your home screen, just change the independent variable to x if you want to graph it. What the calculator does is it will replace all the t's with x's. Okay, alright, now we also want to graph 60, the horizontal line. So let me show you something real quick. let's do this. I'm going to just graph it using the standard window, and then we'll look at the correct way to do it. So if I just graph it using the standard window, bam, that's what you get. Does this help us at all? Nope, it doesn't tell me anything. Okay, it's problematic. So what I want to do when graphing this is I want to make sure that my graph includes this maximum y value, and it also considers this constraint on my x. So I'm going to go to my window. Alright, x mean is 0, I don't care about negative x's because time is never negative, and then to 4, I can put this to just 5 just to make it a little bit bigger, 5. Now my y max is important. I care for when it's 60 or bigger. So in order for it to fit nicely, let me just put it as high as 80. If I put it at 60, the part where it's bigger will be cut off at the top. So I'm going to make it a little bit bigger so I have some room so it fits in nicely, okay? Now check this out. Let's go ahead and graph it. So this is the velocity function from 0 to 5. And there you go. That's the 60 function right there, the second one. So this interval is what we're looking for. This is the AB interval that we're looking for, where it's greater, the upper part. So let's look for this intersection and this intersection. You don't ever want to use trace to find values where functions intersect because your accuracy will be considerably compromised and you will lose your points. Okay, so F5 intersection. There are two intersection points that we're looking for. Let's find little a first and then little b. First curve, second curve, lower bound, you go to the left of the intersection. Upper bound, you go to the right of the intersection. Enter. And we have 1.86618. Okay, so what is that? What did we just find? That's little a. Little a is 1.86618. Now we need to find little b. Okay, the upper bound of the interval where the function is greater than 60. Where is my calculator? Okay, there you are. So we'll do the same procedure again. F5, go to intersect. Where is it? Number 5, F5. First curve, enter. Second curve, enter. Lower bound, any points to the left of the intersection you're looking for, press enter. Upper bound, any point to the right of the intersection you're looking for, press enter. And we're going to get the upper bound in a second. Bam! There you go. 3.51917. 3.51917. Alright, so if you didn't get what we just did, let me just show you. I'm just going to annotate the graph. Okay, so this situation right here, this line is the line 60. Okay, y equals 60. That's this horizontal line. And then this curve right here is your v sub q of t function. Okay, so we're looking for where the function is above this horizontal line. Okay, so it's this interval right here. Okay, so this left intersection is my a, my lower bound, and this is my upper bound. This intersection right here is b. So this interval represents a situation where v sub q of t is at least 60 or 60 or greater, the same thing. Okay, so that's why we did what we did. Okay, now we're done with part 1. Let's go ahead and find the distance traveled by the particle on that interval. So part 2, distance traveled by q on this interval that we just found. You know what? Let's just do this. Traveled. There's something else, another trick I should have done, but yeah, it's okay. Traveled on AB. So I could have stored these two values, but it is what it is. Okay, so to calculate the distance traveled, we're gonna go ahead and use the formula that we just talked about. So distance traveled by V of Q and AB is going to be what? It's going to be the integral from A to B. So, you know what, let me show you exactly. Well, you see, you already have A and B there, so you know what we're doing. So I'm going to be putting those values into my integral expression. Okay, so from A to B. So it's going to be the integral from A to B of your velocity of the absolute value of V sub Q of t dt. Okay. Alright, so let's go ahead and do that with a calculator. Now the shortcut I was going to show you was how to store the intersections from the home screen in the letters, but it's okay. So what we're going to do now is enter the following integral. Let's go back home. We're going to find the integral of the velocity function. I already have it up there, so actually I need the absolute value. So how do we do that? You go to your catalog. ABS is your absolute value. So absolute value of your velocity function, call that. You're integrating with respect to t. Your lower bound, enter up to as many decimal places as possible, 5 at least, okay? So lower bound is 1.86618, okay? And then upper bound is 3.51917. Now if you look at my grouping, I didn't close my absolute value, so let me go ahead and close that so I don't get a syntax error. Alright, so we're looking at the absolute value of V of t, so encapsulate that in your parentheses. So absolute value V of t, and then the variable you're integrating with respect to lower bound, upper bound. Diamond, enter for an approximate answer. 106.109. Now that's, you see the beauty of using V of t, it's easier to avoid making mistakes. Had I entered the original function, it's easy to make mistakes. Okay, so that's the nice thing about storing your functions when you're evaluating, especially when you're using the function multiple times. It's a very low risk approach. Alright, so 106.109, that's our answer right there. So let's write it down. 106.109. So let's write down what the answer means. The distance traveled by particle Q on the interval AB is 106.109. What's the unit here? The unit here is in this unit for distance is meters. Alright, so let's move on to the last one. Before we do that, let's talk about the scoring real quick. Totally forgot. Okay, so how is this scored on the AP exam? This particular problem is a 3-pointer. Okay? Just like the last question that we're about to do right now. You get 1 point for finding this interval correctly, finding that those two intersection points. You get another point for setting up your integral, this definite integral right here. You can put the numbers here, or if you declare these two values, then you can just use A and B. So if you don't declare it here, you have to state exactly what the limits are. But if you declare it, that gives you the right to use the variables that you declared these two values as in any formula. You don't have to write it over and over again. Okay, please show all your calculus. Everything that you're using, you want to make sure you show it. Nothing is implied. Okay, and then you get another point for getting, so 1 point for setting up the integral, and then another point for getting the correct numerical answer, for a total of 3 points. Alright, so part D reads, at time C equals 0, particle Q is at x equals -90. Using the result from part B and the function V sub Q from part C, approximate the distance between particles P and Q at T equals 2.8. Okay, so we're going to be finding the distance between them, basically find a position and then find the change of the position between them at this time right here. Okay, so let's go ahead and write down the steps There are multiple steps involved in this, so let's outline it before we start. So first things first, you want to find the position of particle, the first one, which is the first one, P. Okay, so it says using the result from part B, that's for P. Okay, good. So find the position of particle P. Okay, so we're going to call that x of P at 2.8. So we want to find the position of particle P at 2.8 at t equals 2.8, and that's the same thing as x of P of 2.8. We're going to use the answer we got from part B to get this one, okay? And then secondly, guess what we're going to do? We need to find the position of the particle Q at the same time. Okay, so we're going to have x of Q of 2.8. So we have these two positions. Lastly, what are we going to do? We're going to find the distance between them. Between P and Q at t equals 2.8. So there you go. Okay, so let's get started. First part. Oh wait, before we do that, we need a formula. Formula for position. Remember we talked about this earlier in part B, I think. We said there is position, there is displacement, and there is distance. This one has distance and position in it. So what is the formula for position? Alright, let's take a look at that real quick. Formula for position is as follows. Let me write my position again. So you got to remember that when you're looking for position, you're looking for the position at a particular time. So position, give position at B given x of A. Okay? So whenever you're looking for a position, you always want to have a starting point. Where am I starting from? So I can find the final position. So position at B given x of A. Okay? So the position at B, what's another way to write this? The position at B. The position at B is the same thing as x sub B. Okay? The position at B is equal to the displacement. The reason why I'm choosing A, guess why I'm choosing A? Because we're given x of A. You got to work with what you're given. Okay? So position at B, which is x of B, is the distance, the displacement from A to B. Okay, that's the displacement. Is that all that you look at? No. Plus the initial position, which is x of A. Bam. So there goes this is the formula for position. Now, do you see how this formula relates to all we've been doing thus far? Ladies and gentlemen, this formula right here is simply your displacement, okay? Displacement plus your initial position. That's what it is. Okay, they are all connected. Initial position. Alright, so you really have to have these formulas clear and firm in your mind before you take the exam, so you don't get them all mixed up and get the answers wrong. Okay, so we're going to use this formula twice to find the positions of particle P and Q, and then when we get those answers, we just subtract them from each other to get the distance. Alrighty? Okay, so let's go ahead and get started with one. Part 1, we're looking for position of particle P. So x of P, position of particle P at 2.8. We're given the initial position, okay? So x of P of x sub p of 2.8 is going to be the integral from 0 to 2.8 of v sub p of t dt. This is the displacement plus the initial position, which is x sub p of 0. Okay? Alright. Based on what we got in part B, we are able to use the trapezoidal rule to estimate this. So this is approximately, we know what this is. This was 40.75. And for particle P, at the initial, at t equals 0, what was its position? So let's go back to the problem. It says particle P is at the what? Origin. So what's the x-coordinate of the origin? Is 0. So at times t equals 0, the particle P is at the origin. Okay? Alright, so now that we know that, x sub p of 0 is simply going to be 0 plus 0. Okay, so the position of particle P at 2.8 is approximately 40.75. Part 1 done. Part 2. What is the position of particle Q at 2.8? Well, using the same formula, integral from a to b, 0 to 2.8 of v sub q. Okay, we're using a different function now, plus the initial position of particle Q at 0. Okay? Alright, so we're going to need a calculator to help us out with this. Let's go ahead and fire up our calculators, and then we're going to compute what the displacement is. Alright, so, guess what? We already stored v of q in our calculator. Very convenient. So let's just call it up again just to make sure. So we stored it already, so we don't have to do it again. The beauty of storing functions, right? So let's calculate the displacement. So integral of v of t. Independent variable is t. Lower bound is 0. Upper bound is 2.8. Close that. Let's see what it is. Alright, so it's 135.938. That's what this part is. So the displacement is 135.938. Okay, so we go ahead and subtract both of them now, right? Wrong. What's missing? Do not forget the initial position. We know the initial position of P was 0. Yeah? How about the initial position for Q? Well, this is a different function, so let's look at what it says. It says the particle, it says at t equals 0, particle Q was negative 90. So it was to the left of the origin, so that is very important. So we have to put that here, minus 90. Okay, and then that will give us the correct position, which is 45.93. 8. Now, let's find the distance between them. So part 3, the distance between P and Q. You know the formula for distance, right? The formula for distance is the magnitude of the change in position. So this position at 2.8 of particle Q minus position at 2.8, position at 2.8 of particle P minus position at 2.8 of particle Q. Okay, just take absolute value because distance doesn't consider sign, it's a scalar quantity. Okay, so we're going to have 40.75 minus 45.938 absolute value, and then your final answer is going to be, it's going to be 5, you take the absolute value of that, 5.188. Okay, so let's just write down what this answer means. Particles particles P and Q are 5.188 meters apart. Okay, so there you have it. Thanks so much for taking the time to watch this presentation. I really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming AP Calc exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions or comments about what we covered in this presentation, just put it in the comment section below. And don't forget to subscribe to our channel for updates to other math tutorials such as this. Tons of resources can be found at Mathgotserved.com. Do check it out. Thanks again for watching and have a wonderful day. Goodbye.